apologies. So I need to move to Shai's presentation. Shai, are you ready?
Yeah.
Okay, go ahead.
Okay, so let me share my screen. First of all, hi all, I'm Shai from Israel. Oh, I see that there's another, oh yeah, thanks.
Yep.
Yeah, okay. So let me just share my screen. And let me start this. Okay, so as Noah mentioned, my presentation is on quantum computing and machine learning, basically. Okay, so let me just give a quick intro because I don't really know the level of expertise of the participants. So I just want to talk in a general view and then we'll delve in a bit deeper. So as we all know, the computers we use today are based on principles from physics and principles from electrical, mechanical, materials engineering, and good old-fashioned, of course, straight-up physics are involved in the effort of putting all the pieces together for a computer to work. And the reward we get from all this effort is that computers are, of course, able to perform calculations faster and more precise. But the point here is that even computers have their limits. So what are exactly those limits? So our computers, as we know them today, are based on principles of classical physics, as computation is achieved by performing arithmetic operations using various combinations of simple logic gates. These gates receive classical bits, which are the basic units of computation, perform a certain calculation upon them and return several bits as output. Related fields in computer science try to set limits on how fast this can happen using classical gates. I'm pretty sure most of us familiar with the gates, and we see here like and or and no and not and all of those guys. So the branch of computer science that actually tries to deal with exactly what can be calculated and how fast can it be calculated is called computation theory. So computation theory is basically a branch of mathematics and computer science that deals with some of these limits. And with that, as I mentioned, provides insights on what can be calculated and just how fast can that computation work with regards to its input. And that's a pretty important distinction because we use the input of an algorithm to specify just how fast does it perform its calculations. So using tools from computation theory, one can formally claim and prove lower and upper bounds in running times of algorithms with respect to the corresponding input. So I'm pretty sure most of us, at least, I'm pretty familiar with this concept, but I just wanted to give a like general intro to that concept. So let me just give a quick formal description. It's not really that rigorous and formal to be exact, but just to be on the same page on that issue. So we basically use two notations to discuss lower and upper bounds. We use the big O and the big omega. This is the Greek letter omega notations to denote runtime complexity, upper and lower bounds respectively, as in O stands for upper bound and omega stands for lower bound. This is not a formal definition, but roughly speaking, for just as for this discussion, we can consider an algorithm called A, and for an input of length n, we say that A has a runtime complexity of some O of a function f of n, if A performs a number, this is not exactly rigorous, as I said, but let's just keep it as a number of calculations, which is at most as the order of the value f of n. Like you take n, you give it to f, you get some output, and the number of calculations is at most of that order. And this, the exact same concept holds for the lower bound, which is the omega. We say that an algorithm A has a runtime complexity of omega of some function g of n, if A performs a number of calculations, which is at least as the order of the value of g of n. Okay, so we pretty much, I'm pretty sure that all of us, most of us at least, are pretty familiar with some of these algorithms that are spelled out in here in this slide. Let us just observe the complexity of several of these commonly used algorithms, of course, assuming their input is of length n. So let's assume we have an R-sorted array, and we want to just search for one particular item that we know for sure that is in that array. So assuming we don't have to sort that array, we can just go over the items in the array and search one by one for that particular item. And that just leads us to like the total amount of items for a number of calculations. We just have to go through. This is like the lower bound for a specific item in an array search.
Sorry to interrupt. Idan, can you go on mute? You're making noise on the line, please.
Go on mute.
It was Idan, I think.
Not you, Shai. Continue to speak.
Not you. Continue. It's just me.
Oh, okay.
Idan was.
Okay.
All good.
Yeah, no problem. No, okay. Sorry for that. Is it fine now?
Yeah, I think so. Yes.
Go on.
Okay.
Go on.
Okay. So, like I said, pretty much for us to be able to search for an item, we basically need to search the entire array, which is like, that's why we have a lower bound of the length of that array, which is n. Assuming we want to sort any array without any assumptions, there are several algorithms that do have some assumptions that do perform better than this running time. But assuming there aren't any assumptions, in order for us to sort an array, like in ascending or descending order, whatever, we have to have this, I don't know if you can see my cursor, but we have to have an omega of n log n, like at least perform calculations of the order of n log n, like the multiplication of n times log n, which is of course the logarithm with base 2 with respect to n. We have all sorts of other algorithms that are commonly used, fast Fourier transform. This is called, I didn't really mention it, but this is called linear complexity because it's just linear in the number n. This is what it's called linear rhythmic, sorry. The n log n type. This is a commonly seen function of n that arises in several algorithms. For us to do all sorts of metrics manipulation algorithms, we also have like the running time of O of n to the third power. Note that I did use the omega over here because this is actually the lower bound. And some of these like metrics, Gaussian elimination, multiplication, inversion, calculation of the determinant function, solving a linear system, finding eigenvalues. All of those are can be actually achieved with even lower speeds, but I did use the commonly n to the third power because this is the at most what can be used. I don't know if you like. I don't really know the level of expertise of anyone, but I'm pretty sure like most of us are aware that internet encryption is primarily based on prime number factorization, and this algorithm, the best known algorithm, performs at a sub-exponential time, which is, as we know, not that efficient. Okay, so this is some of the algorithms that we know, and like these are the running times of these algorithms. And the point I'm trying to make here is that some of these algorithms have more efficient quantum counterparts. Now, what does it mean to be quantum? What does quantum actually mean? Well, in physics, quantum is the minimum amount of energy of any physical entity involved in an interaction. This means that the magnitude of a physical property can take only discrete values. This is what the term quantum comes from. For example, a photon is a single quantum of light. Similarly, the energy of an electron bound within an atom is quantized and can exist only in discrete values. That's the whole point of the word quantum. Okay, let me move over, and now we talk about quantum mechanics. So we talked about quantum, and so quantum mechanics is a physical field that describes the properties of nature on an atomic scale. And in contrast to classical physics, where the description of physics okay, let's say it differently. The classical physics is the description of physics that existed before the theory of relativity and quantum mechanics. So it describes many aspects of nature at an ordinary scale, while quantum mechanics explains the aspects of nature at a small, as we mentioned, atomic, subatomic scales. For which classical mechanics is insufficient, as it cannot encapsulate the phenomena occurring at such small scale. So the point being made here is that some phenomena actually happen in quantum scale that do not happen on a classical scale. And that specific, some of these phenomena is exactly what helps us achieve some of these improvements. Okay, so how does it all work? Let me just give a quick intro to the basic concepts of the basic unit of computation in quantum computation, which is called the qubit. It's short for quantum bit. It is the fundamental information carrying unit used in quantum computers. It can be seen to the quantum mechanical generalization of a bit. More precisely, a qubit is a two-dimensional quantum system. Each qubit is just a two-dimensional vector. That's what it is, basically. And the state of a qubit can be expressed as just a linear combination of two, what's it called, like base vectors. These are two base vectors, the 0 and the 1 here with this notation. They're just the basic unit vectors of a two-dimensional space. Each quantum state can express fully in this manner, where alpha and beta over here, the coefficients of these two vectors are complex numbers, such that the sum of their absolute values squared, oh, it's a mistake here. This should be on the outside of the absolute value. The sum of their absolute values squared should be 1. So in the cat notation or the Dirac notation, this is called the Dirac notation or cat notation, this special form of brackets. As we said, these are just two-dimensional basis vectors. So they are shorthands for the vectors encoding the two basis states of a two-dimensional vector space, as we said. So building on top of that, we can talk about system of qubits as we talk about the system of bits in regular computers. So the mathematical structure of a qubit generalizes to higher dimensional quantum systems as well. The state of any quantum system is a normalized vector, as we said, because its norm should be 1. What we saw earlier is actually the norm of that vector. Because it's been 1, so the square root is just not relevant, so it's just 1. Okay, the normalization is necessary to ensure that the total probability of all the outcomes of a measurement sum to 1. We didn't actually describe what the connection is to probability, but we get to that later on. So a quantum computer contains many number of qubits, so it is necessary to know how to construct the combined state of a system of qubits given the states of the individual qubits. So the joint state of a system of qubits is described using an operation known as the tensor product, given two quantum states or qubits, psi and phi, with corresponding alpha, beta, gamma, and delta coefficients. The joint state is just, its notation is like that, and its calculation is by this operation, which is called the tensor product or the Kronecker product, which just means building a block matrix of the inappropriate sizes and multiplying the corresponding values, like take alpha and multiply with gamma and delta, and this is this block, and then take beta and multiply with gamma and delta, and this is this block. So the Kronecker product actually expands the vector with the corresponding sizes. If we have a 2-on-1 vector over here and a 2-on-1 vector over here, this will be 4/1. Okay, so this is like a system of qubits. Okay, let's talk about the measurement and the whole notion of probability. So unlike a classical bit, the state of a qubit cannot be measured without changing it. Like actually measuring a qubit ruins it irreversibly. Like if you measure a qubit, you cannot go back and to the previous state. So measuring a qubit will yield the classical value of either 0, like the base vector that we saw, with probability of its coefficient in absolute value squared. This is like the actual term that describes the probability of measuring 0, or 1 with the exact same concept for the probability of 1. You just take, this is also an error, I'm sorry. This should be the absolute value squared. Okay, so measurement corresponds to transforming the quantum information stored in a quantum system, of course, into classical information, because after we measure, this is not a quantum system anymore. This is a classical system that has classical information, which is either one of the base vectors from the state, like in a 2-dimensional space, is either 0 or 1. In a 4-dimensional space, it can be 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so measurement corresponds to transforming, as we said, the quantum information into classical information. For example, measuring a qubit typically corresponds to reading out a classical bit, whether the qubit is 0 or 1. A central principle of quantum mechanics is that measurement outcomes are probabilistic. It is with certain probability that we get either one of the base vectors as a result. Okay, So let's talk about qubit transformations, as in.
Shai, quick question. So you say that every time we will measure, we can do it let's say every time measure a qubit, we would get a different result?
I'm not. It depends. It is with a certain probability. You can you can flip a coin and you can get heads all the time, but basically you can get different results on different measurements.
Okay, great, thanks.
Yeah. Okay. So a qubit or a system of qubits changes its state by going through a series of unitary transformations. The analog here is that classical bit is just being manipulated by logic gates, as we said before. Logic gates perform all sorts of operation, and logic gates, it's not being spelled out in here because I didn't really want to mix those two concepts, but logic gates have a specific sort of construct for them to be valid. So also in quantum mechanics, each transformation has a specific construct. What is this construct? So a unitary transformation is described by a matrix U with complex entries. And the matrix U is called unitary if this equation here holds, as in U times U dagger is equal to U dagger U equals to I. Where, let me explain each item here, where U dagger is the transposed complex conjugate of U, as in you take U, you transpose it, and then you apply the complex conjugate to each element of U. It's also called its emission conjugate. And I is just the identity matrix. Of course, U is NLN is like square, like it's of a certain size n, and on rows and columns both. So the identity matrix here I is of course of the same size. Okay, operators acting on different qubits can be combined using the Kronecker product, as we said. The Kronecker product applies for looking at two qubits together. So also these operators can be combined using the same Kronecker product, as in if we want to do also like successive operations on a qubit, we just multiply the Kronecker product of these operations. For an n-qubit system, the set of physically allowed transformations, not including measurements, consists of all 2 by n times 2 by n unitary matrices. This is just technical looking at things. In practice, the transformation is effected by using a combination of unitary transformations that act only on 1 or 2 qubits at a time. By analogy, as we said, the classical logic gates, like NOT and AND, such basic unitary transformations, which are built up more complicated, which are used to build up more complicated n-qubit transformations, are called quantum gates. Let me move on to quantum computing. So quantum computers use effects such as quantum coherence and entanglement to process information in ways that classical computers cannot. Using quantum gates, quantum algorithms can, in principle, outperform the best known classical algorithms when solving certain problems. This is what is known as quantum speedup. So looking at the algorithms we mentioned before, for example, for an unsorted array search, Grover's algorithm can do this task with a runtime of O of square root of n, which is better by a square root speedup of the best known algorithm, as we mentioned before. The forced Fourier transform can do its calculation by this function, which is, if we recalled, the best classical algorithm did this with n log n. So this is actually exponential speedup. prime number factorization, as we know it, as we know is the base of the whole internet, is also as a sub-exponential speedup, because this is the function that that actually describes its runtime. And also least squares, matrix operations, and all sorts have an exponential speedup. So this is the last slide. Basically, with machine learning subroutines, as in Bayesian inference, only perceptron, least squares fitting, Boltzmann machines, principal component analysis, and even support vector machine, all of these have speedups of these orders. So, meaning that those have a speed up of an exponential time. All of this that it says log n, and these have a speed up of square root of time. So this is, if n gets really large, that can really improve calculations and practically change things quite a bit. So basically, this is the concept of quantum speedup and its applications to machine learning in a nutshell. Questions?
I have a question generally, so maybe you can answer, maybe someone else in the media call can answer. Anyone knows where, I know that there are a lot of efforts in the industry or in the universities to actually implement like a quantum computer. So anyone knows where the community is now in these efforts? What was achieved until now to build a computer?
I'm doing a course on quantum computing as we speak, and basically what we learned in the course is that quantum computing is pretty, as a theory, is pretty advanced, because quantum algorithms have risen even in the early 90s, but quantum computing implementations are still pretty far away, because actually building a quantum computer from a physical point of view is still not being done on a scale, and only being done at a research level, and even so at a very still limited manner. So to answer your question, this is still not being implemented fully, but all of these theorems and understandings have been proven mathematically. So one just needs to actually have the I don't know, the power and like the resources to build a quantum computer, and maybe even produce it at scale for us to actually witness all of these improvements.
Did you play with some site like, I know that there is the quantum experience in IBM, and did you experiment? Because as you say, like in terms of algorithmic, it's interesting, right? It's a new way of building algorithm. So it's kind of interesting aspect. I know we can simulate, or there is some access. Did you check that, or did one of you guys play with this type of algo or simulator?
Well, I'm doing, basically at this time, I'm doing just a purely theoretical mathematical course. And even the lecturer said that he didn't even have the chance to apply any of those algorithms, so no. But
yeah, okay.
Yeah.
But there is in IBM, there is a site like create your, and you can create your first quantum circuit or this type of thing. So if you guys want to play, that's maybe interesting to see, but just people who are curiosity. But Google and IBM are kind of racing together, not together, each other, right? That's what we have seen in the news.
That's pretty much what my lecturer also said. And he did mention the IBM side, but I didn't really have the chance to check it out. But yeah, it is an ongoing race at this time. Yeah.
Shai?
Yeah.
So from the little I know about quantum physics is that the qubit can be like in a superposition where it can be either one, it's like both 0 and 1 at the same time, something like this. I didn't hear you mention it. So how does it plug into what you described?
Yeah, this is actually, I didn't really delve into that, but actually this equation actually states this exact statement that you just mentioned, because prior to you doing actually a measurement, this quantum state psi is actually 0 and 1 at the same time. You just after you measuring it, it will reduce, actually collapse, actually ruin itself and become a classical bit, which is either 0 or 1.
Yeah.
It's not, I'm sure I know that it doesn't really answer your question fully, because this notion is not it's pretty elusive. And,
yeah.
Yeah, but
in terms of
it used to be black and white, Idan, and now the answer will be depend.
Yeah. Yeah, like quantum physics and all. But in terms of irons, like the computer material itself, so it's also different from classical computers, right? Like with silicon, semiconductors and such.
Yeah, exactly.
Am I wrong?
Because of this, because you want to implement this notion, you have to, of course, use different, actually physical instruments, and this is exactly the thing that is keeping us from achieving quantum supremacy, as the notion that Google and IBM are talking about, because you have to use different materials, and this is exactly the issue.
So Shai, let me just ask one question about the readout. So what you mentioned is basically the outcome, it's basically a probability. So once you basically do the computation, then you have a huge factor of, of the qubits, and you need to collapse them. So how is the readout basically done? So you need to repeat the experiment thousands of times, so you get the probabilities of the outcomes in the end, or you just collapse it once, and then you get zeros or ones, and this is what you get. So how is basically reading out the outcomes? How does it work? So do you need to sample it as a distribution many times to get those probabilities, or you're just looking at the collapsed state, whatever comes out?
This is actually a good question, and I didn't really talk about it, but from a theoretical point of view, as we just talking about it without actually implementing it, we just talk about some distribution that we talk about before, that we agree upon beforehand. But yeah, in actual systems, you actually look at the collapsed state and deduce the probabilities from that. That's what's being done. It is, it has some measure of inaccuracy, but it's, as from my understanding, from what the course spelled out, this is what is done today for us to be able to talk about these coefficients and the probabilities.
Okay, so potentially collapsing it once or a couple of times, then deducing what the probabilities were. That's right.
Yeah.
Okay, thank you.
Great. Thanks, Shai. I think, David, we're out of time. Great presentations. I will post them in the Confluence page, the recordings, as well as the presentations themselves, the slide decks. And then if someone else has questions, of course, we can pass them to David and Shai. Thanks, everybody.
Thank you.
Thank you.
Thanks. Bye.
Bye.
Thanks. Bye-bye.